Okay, calculus integrals, part 2, day number 3 on improper integrals. Now, what makes an improper integral as opposed to a definite or indefinite integral? Here's your indefinite integral. No limits of integration. Here's your definite integral. Limits of integration. And here's your improper integral. It's got one real limit of integration and one limit at infinity. Let's get started with improper integral. Alright, so let's see if we can evaluate each of these integrals. So this integral right here would actually be 3 times the integral from 1 to infinity of 1 over x dx, which is familiar to us, which is 3 times the natural log of x evaluated from 1 to infinity. So how do we evaluate these when we have an infinity involved? Well, what we do is we assign a variable and then we take a limit. So let's take the variable b and then we assign infinity this variable. Okay, then we do a direct substitution. So the limit as b goes to infinity of 3 ln of b minus 3 ln of 1 Well, as b goes to infinity, what does this term turn into? Well, that would be 3 times the natural log of infinity. Alright, and this term right here, well, natural log of 1 is 0, so 3 times 0 is 0. Therefore, 3 times the natural log of infinity, what's happening to the natural log as it goes to infinity? Well, it keeps climbing slowly, but it will still go to infinity. So this will be infinity minus 0. 3 times infinity is still infinity, and therefore we cannot estimate or come up with a finite value for the area under that curve. And actually, if we look at the original, the graph of the original, I think it was 3 over x, would look like this. Right, if we went from 1 out to infinity, we're not able to come up with a value for that area under that curve, therefore it doesn't exist. Okay, so let's switch it up a little bit. Let's go from 2 to infinity of 2 over x squared. So I'm going to rewrite this in a different way. I'm going to write it as 2x to the negative second dx, which will be x to the negative first times negative 2, evaluated from 2 to infinity. And actually I'm going to rewrite that yet again. I'm going to write it as negative 2 over x, evaluated from 2 to infinity. See if you can take the steps to simplifying this and evaluating this improper integral. So I get 1. You'll see that the limit as b goes to infinity of negative 2 over b will eventually go to 0. And if we take 0 minus a negative 1, we get 1. So if we were to look at a graph, it's pretty amazing how this works, but a graph of 2 over x squared will look something like this as well. As we go from 2 to infinity, the area under that curve is going to equal 1. It's amazing, and we're going to get to more of that as we get into sequences and series and all that good stuff in the chapters to come. Alright, so some definitions of improper integrals of this form right, from constant to infinity of f of x dx. You can read this on your own time, just some properties that are available to you there. Let's get started with a couple more examples. All right, this is a really important example. A couple of cool things show up. So why don't we do a quick setup here? Why don't you go ahead and set up, I think we're going to use integration by parts. Get your u and your dv and your du and your v, and then let's get to a simplified version of integration by parts. Okay, so here's what I've got so far. I'm going to clean this up. It's going to make a lot more sense here in a second. I'm going to put negative x over e to the x. And then these two negatives I'm going to have cancel. So that would be plus the integral from a to infinity of e to the negative x dx. And all I have to do is integrate now e to the negative x. So I get negative x over e to the x minus e to the negative x. And I'm going to do one more thing here. Negative x over e to the x. And I'm going to turn that into negative 1 over e to the x. And I'm going to evaluate that from a up to infinity. Okay, so let's do that. So I'm going to take the limit as b goes to infinity of negative x over e to the x minus 1 over e to the x from a to b. Alright, so what would that look like? That would be the limit as b goes to infinity of negative b over e to the b minus 1 over e to the b minus negative a over e to the a minus 1 over e to the a. Alright, so let's see what happens here with b. If I plug an infinity in here for b, that's going to become 0. But if I plug an infinity in here, I'm going to get negative infinity over infinity, which is a problem. If I get infinity over infinity, that is an indeterminate form, which tells me I'm going to want to use L'Hopital's rule. Okay, so I'm going to use L'Hopital here real quick. And I'm going to do some simplifying around it. So this would be the limit as b goes to infinity of, I take the derivative of the top, derivative of b is 1, derivative of the bottom is going to stay the same. I already knew that was going to be 0 here. Minus, I'm going to combine these two. That'll be negative a minus 1 over e to the a. And so now as I take the limit as b goes to infinity, this will become a 0. Therefore, I get 0 minus 0 minus negative a minus 1 over e to the a. So it looks like this negative distributes to both of those negatives, and the area under that curve from a to infinity would be a plus 1 over e to the a. So anytime you're taking limits within that integral, potentially you could need to use some form of L'Hopital's rule depending on if you get 0 over 0, which is, it could happen, and infinity over infinity. So let's try a couple homework problems. Okay, let's try these two. Let's focus on A first. This looks extremely close. Right? This looks extremely close to 1 over x squared plus 1. Right? Now let's talk about the rule that we found out just the other day. The integral of 1 over x squared plus a squared dx is equal to 1 over a arctan of x over a. Right? So that actually applies here, because this is, in that general form, exactly what we have. But what we're going to be doing is taking the limit as b goes to infinity of this thing, arctan of x over a from a to b. Alright, so let's evaluate. Okay, so here we go. So this will be the limit as b goes to infinity of 1 over a arctan of b over a minus 1 over a arctan of a over a. Right? A over a would be 1. Alright, we gotta look at, real quick, gotta look at the arctangent graph, which we talked about just a few days ago. Or it felt like it. Here's the graph of arctangent. What happens as x goes to infinity? Well, the graph approaches pi over 2, right? Approaches that. Therefore, this would equal, okay, this piece right here, the arctangent of infinity would be pi over 2. So this piece would be 1 over a times pi over 2. Okay. Over here, what's the arctangent of 1? Okay, so the arctangent of 1 is an angle, and that angle is pi over 4. Okay, so then we have minus 1 over a times pi over 4. Okay, so if I factor out a 1 over a, I have 1 over a times pi over 2 minus pi over 4. Pi over 2 minus pi over 4 is pi over 4. So I get 1 over a times pi over 4. Bad color choice. So I get pi over 4a. There is the area under that curve from 0 to infinity. Okay, let's try this one. Ooh, I like this one. I see a u substitution coming on. I see u as 1 over x. I see du as negative 1 over x squared dx. So I see this nice 1 over x squared dx, but I don't see the negative, so I'm going to account for that. So negative du equals 1 over x squared dx. Okay, so then that means I have the integral from 1 over pi to infinity of sine of u du. So if I integrate, I get negative cosine of u. Evaluated from 1 over pi to infinity. I want to sub back in and get rid of u. So it'd be negative cosine of 1 over x from 1 over pi to b. Let's throw that limit on the front of it too. Okay, get rid of some of that. Okay, I'll put the limits as b goes to infinity of that. Alright, let's evaluate. Actually, if you would, you can go ahead and pause, and I'll do this on my own. Okay, so I get this. If I send b to infinity, what does this become? Well, 1 over infinity becomes 0. What does 1 over pi become? Becomes pi. So I get this, the limit yields me negative cosine of 0 minus negative cosine of pi. let's evaluate that. Cosine of 0 is 1, so I get negative 1 minus cosine of pi is negative 1 as well. So I get minus a negative 1. Okay, so if I simplify, these will chop and cancel. It looks like I get negative 2. Oh my goodness, I just caught something, because that area doesn't make sense being negative 2. See this negative right there? I forgot to carry it along. Therefore, I could have carried it along all the way and would have made this a positive 2. Alright, I'm glad I caught that. Okay, let's do one more example. Actually, I want to do... Alright, I'd like to do this problem right here, which is sneaky good. But if I rewrote this, or actually if I used u substitution, said u equals tangent of x, then du would equal secant squared x. So then this becomes a very easy integral from 0 to pi over 4 of, right, so the dx and the secant squared are taken care of, so then it's just u cubed over, oops, it's just u cubed du, which is u to the 4th over 4, right, which now if I evaluate would be tangent to the 4th x over 4. And as I evaluate that from 0 to pi over 4, tangent of 0 is 0, and tangent of pi over 4 is 1, so it's 1/4 minus 0, which equals 1/4. Pretty easy. It doesn't look as easy when you look at it there, but it comes out to be pretty nice. Alright, that's it for improper integrals. We'll move on tomorrow to a new topic. Have a great day. See ya.